Hello, everyone. Thank you for joining us today. Today we'll have a webinar dedicated to hardware reverse engineering. And we will provide here some and discuss, of course, some interesting insights for both engineers and managers of different levels. First of all, I would like to ask you, our dear guests, just to type plus in the chat so we'll know that you can hear us, that you can see us. You have a chat here, so please provide pluses here. That really would help us to understand. Is anyone could participate in this webinar with us, of course. So far we have only one plus. Okay, it seems that we still have people keep joining us. Let's give them 3 minutes more. And then we'll start our today's topic and all the discussions related to our webinar and hardware reverse engineering. Okay. Yeah, we have more pluses in our chat, so I think we can slightly start here. First of all, let me please introduce myself. My name is Michael Teslia. I'm a program manager at Apriorit, a cybersecurity company with more than 2 decades of expertise in this field, and I'll be your host today. While people keep joining us, I just would like to tell a couple of words related to that our webinar will be recorded and accessible from our website and social media. And of course, regarding our today's plan, first of all, we'll have an approximately 30 minutes lecture. And after this lecture, we'll have even more. We'll leave a window for all the questions and discussions that may appear during our lecture. So please do not hesitate to leave your questions in the chat, and we'll tackle them all after the lecture. Let's proceed. And of course, generally talking about reverse engineering, I think everyone has dealt with these, especially with software reversing. Haven't you? I think so. And so let's check one more time our chat, how our chat works. And please text whether you have ever dealt with reverse engineering on your project. Just please type plus or minus. We'll share all this information, whether we have and approximately how many projects do we have here related or dealt somehow with reverse engineering. And of course, you might have reversed Windows programs, network protocols, or even web APIs, and so on. But what is especially hardware reverse engineering and how these could help us to save time and money, of course. Let me provide one real-life example. And this was not a very simple task for us, of course, as we have been working on this project more or less around 3 years. And don't be scared, of course, because this project resolved our problems, our main problem, much more earlier than these 3 years, but it is what it is. And this was actually a reversing of a medical device for liposuction, which used to use cards to run a treatment process. And around 3 years ago or so, the manufacturer of these cards terminated their business. And this is a pretty common risk, isn't it? And of course, our customer remained with a lot of such expensive devices and patients and cards without possibility to top up these cards, I mean, of course. And this is really scary because he was not able to proceed with treatment of his patients. And have you ever been in a similar situation? I really hope no. And of course, upgrading everything to use the new devices and new cards, it is almost impossible task. And we applied here different hardware reverse engineering practices and approaches to research what happens here under the hood. Under the hood of these devices, and made them work again with custom cards, which can be simply produced not by the outsourcing companies as before, but can be produced just directly by our customer. So actually, hardware reverse engineering here, as we see, can really save a lot of your resources, and this really works in the real life. And just one more small request. Please type which percentage approximate of your projects involve reverse engineering, actually. This also would be very useful and interesting information for us. So let's proceed, and now let's plunge into this with our speaker. Ladies and gentlemen, please welcome Serhii Nadtochii, a principal researcher at Apriorit with more than 8 years of expertise in this field. And of course, today we'll talk about what is hardware reverse engineering from technical perspective, of course, differences between hardware and software reverse engineering, what exactly can be achieved here. Then we will consider different techniques of hardware reversing. Then we'll consider and review examples of reverse engineering projects. And then we'll, of course, review and discuss which risks and challenges we may face and how to mitigate them. So, Serhii, this stage is yours.
Hello, everyone. Yeah, thanks for introduction, Michael. So, yeah, let's begin from the general overview. So, what is a hardware reverse engineering? So, it is in general a process of research and investigation, some black box device, understanding and gathering information about its internal work, algorithms, processes inside, design of the device and components, and etc.
Okay, I have here a small request to our audience. Just please, before we proceed, of course, and name, as you see them, two key differences between hardware and software reverse engineering. Just please type in chat, don't hesitate to do this.
So, yeah, I can continue. So there is similarities and of course differences can be between usual, maybe more familiar, more known software engineering and hardware reverse engineering. So the software reverse engineering mostly focuses on the researching of the algorithms and the logic of the software components. But in a difference that hardware reverse engineering also requires understanding and gathering information about the physical components of the device, about some PCBs, its design, and restoring the initial information about that. So in this section, I want to talk about the, I would say, maybe common workflow in hardware reverse engineering and the tools and knowledge which we should know to perform successfully hardware reverse engineering tasks. So the first one point, it is knowledge about the PCB design and analysis. So it is good to know how the PCB is designed, so to understand how to investigate that, to gather information about the device, splitting it into some the general components. For example, like we can find some power circuit, we can just split that segment, and we will know that we not so interested in that part, but we can find more interesting places with microcontrollers, memories, some communication interfaces like internal or external. And yeah, so this information will be useful on the first stages for the like initial analysis, decomposing of the device, and then identifying the key components. The second one topic, it is knowledge about basic digital electronics. So it is good to know such topics like TTL level logic, about pull up, pull down resistors, logical, what is logical 0, logical 1, what is inverted signals, direct signals. And this information will help us to understand the connections between components, to identify some interfaces and protocols, to understand some allowed voltage limits and power limits. So, for example, if you have some components which is talking in a 3.3 volts, and you will connect some gear which communicates in a 5-volt logic, so you can probably blown out some target components because they can be not 5-volt tolerant.
Okay,
Uh,
so actually, this is a bare minimum we need to understand of electronics to start debugging.
yeah, I would say it is like basic theory minimum to like perform some basic analysis of the device and try to not to kill device and understand how it can work. But yeah, in the future we will need like more advanced knowledge and the tools to understand how to perform such tasks. So yeah, the next topic, it is more about tools. So one of them, like crucial device, it is a multimeter. So it allows us to perform some basic measurements like the voltage, resistance, current, uh, allows to trace wire paths. It is very useful also on, I would say, maybe on all stages of the hardware reverse engineering, because on the first it can help, for example, to trace some wire paths on the PCBs, because at current days we have very complex and expensive PCBs. They can be multi-layered, for example, 6, 7 layers, and you cannot even see some layers because they are between internally in the PCB. So you cannot see it with a human eye. And this is kind of tools which help us to trace that wires. We can point into places and just to understand uh, these points connected or not. And also it is good to measure some basic parameters, as I said, like the voltage, understand which voltages allowed on some ports, interfaces, or maybe on some external places of the device. The next thing, it is a logic analyzer. I would say it is more advanced device because it allows us to collect information from some digital protocols, analyze them, and also it is good to identify some hardware interfaces and protocols. Um, so, for example, you can see with a multimeter just only like the static information, like you have some voltage or not, but logic analyzer allows you to record some, for example, timeline and understand what values was on this interface. So we can collect some digital information and the future analyze it in the details. And the next one, I would say even more advanced, it is oscilloscope. This device will help us to find and analyze any type of the signal because it can analyze like digital signals or analog signal, any form, maybe some spikes, and do some advanced like calculations with the internal, based on internal features of this device. So yeah, it is good to use oscilloscope in the situations where you need to do some precise measurements. Like for example, it can be some clock line where you want to understand on which clocks with which delays devices communicate, or maybe just analyzing some any form of the signal to understand how it changed. Also, like we have in a usual software world, we have compilers and of course software debuggers, which allows us to build the firmware and compile it, debug, understand how it works on a computer. But similar, we have in the hardware world device programmers and debuggers. They also used for the usual development of the hardware, and we of course can use it in a hardware reverse engineering tasks. So these devices usually involved in the process, for example, like programmer used for the uploading firmware on the microcontroller, updating some configuration bits, flashing some internal memories like EEPROM, and also it can be used to download firmware from the device. So yeah, it will be very useful, but you probably need to have several of these devices because each manufacturer develops its own ecosystem. So you cannot like take, for example, AVR programmer and connect it to the STM32 microcontroller. They will be not compatible, and you need to have maybe several tools for uh, dealing with this task. And also, debuggers were useful to like attach to the microcontroller and analyze its internal state just to understand what's going on in the registers, in the memory, what may be processed incorrectly.
Okay, just to summarize, Sergey, so actually we can do our work here, I mean debugging and everything, just using several of such devices, not all of them you just listed. So several would be enough?
I mean, several programmers or debuggers we need because there's a lot of manufacturers of the microcontrollers, and if you probably have some complex PCB which utilizes different microcontrollers from different manufacturers, you probably will need different devices because there is no universal like debugger or programmer. Of course, there is maybe can be some unofficial like custom devices, but they probably will be very expensive. Like they can support a lot of microcontrollers, but I think better to use the original tools because they behave better in a real world based like on real examples, I would say.
Oh, yeah, of course, because I've just recalled one interesting case from my experience. When we used a board with just 8 LED lamps for debugging the keyboard firmware instead of a debugger with UI. So this was a quite interesting experience when we used just these lights, which were representing the digits in binary formats, and we really base our theories and debugging on that. knowing only some of the binary error codes. And of course, to our guests, please type in chat which challenges you're mostly facing during debugging on your projects. These could be both hardware or software projects. And also we'll show these responses if they are really interesting and insightful. Okay, meanwhile, we can proceed.
Yeah, Michael, that's a good example of developing your custom tools for debugging and analyzing something. But yeah, we'll talk about that in a short moment. So yeah, let's go on. The next one, as I said, the custom devices. Uh, it is good to have such devices, maybe like Arduino, Raspberry Pi, or maybe some dev kits, or even maybe some other tools, uh, so they can speed up our process in prototyping of some device and researching some complex tasks, complex states, replicating them, and other things. I mean, it is it will be more expensive to design and develop your custom device for like specific things. Maybe you will use it for the week of the research or two and maybe throw in the trash. So it always good to have some tools like Arduino, Raspberry Pi. You can simply just write the firmware, uh, try some new ideas, some communication with other devices, and it will be very useful and fast in comparison with like custom development maybe. And there is a big chance that you might develop some PCB. It can be failed like in the design. You can check it only if you like assembled it fully. So yeah, it can take a lot of time to try and repeat. Um, the next one, the digital protocols. There is also good to know about them, at least about some basics like we have UART, SPI, I2C, also sometimes one wire. So there's like maybe most common the serial interfaces, which is used for some internal and maybe sometimes for the like external communication between devices. So we will go shortly just to understand what's the difference. So UART, it is, for example, the serial interface, which is used for the point-to-point communication. SPI, serial peripheral interface, it is a synchronous interface which works in the format of main secondary device and communicates with a clock, and I2C interface, which also works as a main secondary addressable bus. But the interesting thing that in I2C, we need to send specific address packet to choose the device with which we want to communicate. But in SPI, you just need to pull up the chip select pin just to choose device with which you want to communicate. And yeah, the digital protocols, uh, good to know for the situations where we want to analyze application layer protocols. So I can give I think example with the OSI model. So we all know that we have like TCP, UDP packets, and they are standard, common. Everyone knows about them, like their structure. So the same thing, like here you can use UART, SPI, and I2C as a TCP or UDP packet. But on top of it, you also probably will write, while developing your device, you will write some application layer protocol. So you will send some streams, some packets, some bytes, and there's your idea how you like split them, separate. So yeah, this is good to know about these basics to go on the, I would say, on the next step to understand more high-level protocols.
Mm-hmm. But do we have any other protocols for communication on that level?
Mm, I can say maybe in more like advanced devices, you can find a CAN bus. For example, in automotive, it is often used, or maybe in some drones, UAV, like this. And yeah, this is also very good, like the interface, which is very stable to the noise environment, and like this. And for example, it can be also some custom uh, interfaces and protocols, like it can be some parallel interface, like you can just connect 8 lines between two microcontrollers and you now have the parallel interface, which will transfer 8 bits of information for the one clock of the CPU. Uh, Maybe the most popular and most known example as a parallel bus, it is a PCI Express from the computer world. So you know that number, for example, PCI X8, 16 or something, it is just how much parallel lines you will use in a PCI. And there is the reason why is if the number higher, then it works fastly. So yeah,
Mhm.
that's it.
Yeah, yes, of course. Thank you.
So yeah, move on to the next step. Um, so yeah, uh, after we know all these points uh, and we know all this knowledge, we can step closer to the usual software reverse engineering. So by applying these points in some way, not exactly like direct way as we go through them, so we can get closer to the software reverse engineering, where we can, for example, analyze some firmwares, some data streams, some data packets already captured by applying this knowledge and tools. So yeah, and let's talk about right now what can be achieved with the hardware reverse engineering. So, for example, it can be such tasks like the security and the penetration testing, extending the lifetime of some legacy devices, like if it's out of support by the manufacturer, analyzing infringement of some intellectual property violations and legal analysis, enhancing the compatibility with the other devices and protocols, like in cases where you want to make this device compatible with some other kind of devices, you need to perform reverse engineering in the software and the hardware. Adding some new features to the existing device just to maybe be actual on the market and do the more advanced tasks. Um, Fixing bugs or some on some legacy devices, which is also can be out of support, or even like reverse engineering partially or completely the firmware of some device and the hardware when you lost all the source codes and documentation to the device. So like restoring it to the last stage on which we have like device in hands to the source code and maybe even adding the new features to this information.
Hmm. And which area on the list is the most complex and unpredictable?
Mm, which is most unpredictable. I would say maybe it is adding of the new features because it will require doing some reverse engineering in the software and hardware, taking into account the available memory on the microcontrollers, on some memory blocks, maybe even thinking about the size of the some hardware patch. Is it fit in the current enclosure of the device or not? So yeah, I think this will be the complex task.
Okay, sounds reasonable.
Yeah. So yeah, let's move on. Let's talk about the hardware reverse engineering techniques. So we got through the points about the knowledge and tools, which is good to know for the hardware reverse engineering. And now we can apply them in different techniques to achieve some results for the performing reverse engineering. So it can be some kind of black box analysis where we just feed some pre-crafted samples of the packets to the device and just analyze how it reacts in general on some uh, information. So it is good to use maybe when you have completely no understanding about the device and the data which it operates on the interfaces. So it is good technique on the first stages. Uh, on the other one, it is good to apply some data sniffing. It can be performed, for example, with a logic analyzer, oscilloscope, or some other tools. So it is a process of capturing some data between the components while they operate, while the device is working. So we can sniff some data, store it, and maybe in future analyze it somehow in different ways. Data injection and proxying. It is a similar process technique to the previous one because we also apply here data sniffing, but also we apply here uh, decoding of the data bytes of some packets on the fly. We, for example, interested in some small piece of the information which we want to change. We don't want to change the complete, for example, uh, uh, stream or data packet, and we can find that interesting piece, change only that thing, then convert again the data packet in the stream and send it to the other device. So it will not see any changes. Um, uh, Other technique, it is a simulating. So it is also some sort of the feeding of the specific packets with some values to the inputs of the device. So for example, you have some device with a temperature sensor and some other bunch of sensors, and you want to fix the device. So I think it will work in one, for example, temperature. So you can understand the how it communicates with the temperature sensor. Just connect some, I don't know, Arduino or Raspberry Pi and feed that information as a sensor, for example, 25 Celsius, and the device will think that it stays in a single temperature. But now you can try to manipulate the other uh, sensors, other interfaces, and check how it will behave on changing some specific data while the, for example, temperature stays focused on hold for the whole time. Mm, the other one technique, it is firmware dumping and emulation. So yeah, it will require our, as we said, the debugger and programmer. So we can in with these tools download the firmware from the device for the future static and dynamic analysis and maybe emulating some parts of the firmware or the whole firmware if we're interested in that. And the last one, maybe I would say most advanced, it is a microcontroller voltage glitching. It is a process of the switching turning off the power for the microcontroller for the very short period of time, very short and precise period of time. So in that way, we can glitch the microcontroller so it can try to execute unwanted branch. For example, we can bypass some protections. So like it can operate incorrectly in that time when it have not enough the voltage. So we can try to glitch it and bypass some protections, for example. But yeah, this technique requires very precise tools, timings, and a lot of effort to achieve that.
I have here a small question to everyone. Which debug techniques are most common for your projects? And please let us know in chat. Also, like just to recall you that we can use our chat. It is, of course, open for all the questions and topics you would like to ask or to discuss. Please don't hesitate, type and post anything to chat that you would like to discuss with us further right after the presentation, right after the lecture. And we'll tackle everything that we'll have in our chat. So please use it for all of your topics you would like to raise.
So yeah, we can move on. So yeah, let's talk about the examples of hardware reverse engineering projects. Uh, we have a lot of them, successful projects, but we just choose, for example, two of them just to fit our timeline. So the first one, it is a project related to the reverse engineering, the protocol of the smart batteries. So the idea here to design the compatible charger to these batteries. So we involved in that process to understand this protocol of these batteries, because it is not enough just to connect them to the charger, apply some voltage, and it will start charging. So should be provided some initial communication in the battery to trigger that process. And also it was useful protocol, so it also allows to get some data about battery, for example, the overall voltage on the cells, current, and even the cycles of the recharge of the battery. And the second one, which is mentioned already by Michael, it is reverse engineering of the legacy medical equipment. The idea here to extend its time life, because it was dropped by the manufacturer, and there's a lot of devices which still can work. They are good from a technical side, but yeah, and we involved into that process to reverse engineer and analyze its internal protocols, how it works with other devices and with the cartridges, and to extend it lifetime to allow it to work next and recharge the cartridges. Yeah, so
Um,
hardware. Yeah,
yeah, I just would like to say that this
yeah.
is probably would be the largest part of our today's lectures. I mean, the risks and challenges, but never mind.
Yeah, yeah, yeah. So of course, hardware reverse engineering can be very risky and challenging, because there's, as in the software reverse engineering, it can take a lot of time and a lot of unpredictable some new things. So let's talk about the risks and challenges, and in the next slides we'll talk how to mitigate that risks. So the first one, it can be firmware obfuscation or encryption. It will increase the time of the analysis and make it harder to analyze the firmware. And yeah, it can be longer. Um, Also, it can be some anti-tamper protections of the device, some production mode disabled in the device, or some disabled debug ports and capabilities, some hardware key storages, firmware integrity checks, which makes harder injecting some parts of code into device, some secure boot or trusted boot protections. Also, it can be damage to the device while performing the hardware reverse engineering tasks, or even data corruption of the device. So yeah, and how to mitigate these risks. So the first one, I would say it is good to have some pre-research stage on which we can understand the general domain of the device, its specifics, do some basic pre-research like create some diagrams of the components of the device. So just general understanding and understanding some potential risks which can be related to such a device. The other one, it is good to have some, for example, environment simulation, where we can simulate some states, some environment for the device, so it will not turn on, for example, some protections, some self-locking mechanisms, and so on. Also, it is good to apply some like non-invasive techniques like some monitoring, sniffing, visual inspection, and so on. So also to not trigger some protections of the device. The next one, it is proxying and injecting some parts of data. Of course, just not to try overwrite completely some information and data streams, but just to try change little parts of it to understand how, in general, device can process, decline, or accept your data. Uh, it is also good to have some precise tools and devices, because otherwise, if you measure some uh, values and you get incorrect values, so probably you will do, of course, incorrect calculations, incorrect measurements can lead to the some damaging and the other bad stuff with the device. Uh, the next thing, it is good to have some expert knowledge in the area. So, for example, it can be some, as we said, medical equipment, some batteries, like how the charging process happened, and so on. So, just good to know some specific of this field. And the last one, but also very important, it is to follow the protections with electronic static discharge, over voltage, and over current protection, just to not allow, for example, device to draw a lot of current, just to burn itself, and to check the electronic static discharge, just not to kill device by just touching the PCB or something.
Okay. Did you have any accidents in your practice of killing the devices?
Yep. Yeah. I have one. I had recently such accident, so I just killed the charger for the batteries. I didn't check that it is connected to lab power supply, and I just turned it on power supply, and it just killed by the starting voltage. It just spikes a lot and just burned my charger. So yeah, it happens.
Oh, yeah. And of course, sometimes we win and sometimes we learn.
Yeah. Yeah. So yeah, that's it. Maybe you have any questions?
Thanks a lot, Sergey, for your lecture. And actually, in chat, we don't have so many questions. The first one was from Jerry. I'm showing it on the screen, and this is related to whether the video recording will be available after the webinar, after the lecture. And the response here is yes, of course it will be available. Everything has been recorded and will be shared with all the registrants during next week. So yes, here we are good to go to review everything that we have recorded here. Another one we also have from Jerry, who started his career as a C developer and is going to work on Arduino projects. Yeah, it's a very good news, Jerry. Good for you. And we could wish you good luck on all of your further projects in the future. That's nice. Hope you will enjoy this interesting world and interesting way you decided to go. And it seems that we don't have really much technical questions here. Of course, yeah, we understand that this is a pretty difficult topic. So it's not easy to understand sometimes maybe, but if you have any further questions after the webinar during some period of time, of course, you can always contact us using this contact information. Just please feel free to reach us out directly if you have any questions or anything. So please do this. You have all the contact information on the screen here. And so far, we still haven't had any new questions coming to us. So I just would like to say many thanks for everyone who joined our today's webinar. Thank you, Serhii, for such interesting and insightful lecture. I hope this was very insightful and interesting, not only for us, but for everyone who has joined our lecture and our webinar in common. And of course, thanks for your time. And if you have, again, any further questions, please feel free to contact us using the information provided on the screen. And thanks everyone again. Have a great day and have a great rest of the week.
Yep. Thanks,
Bye.
everyone.
Bye, everyone.
Bye.